thank you so much for giving me the opportunity to present our work. So this work has been done in collaboration with these people. So, okay, let me start. So the focus of my talk will be largely on the WIMP dark matter candidates, which are the weakly interacting massive particle candidates. So experimentally, we know they can be probed at either direct detection, indirect detection, or they can be probed at colliders. So whenever we are searching for some new physics, so we have to look for new physics above the standard model background, right? So we need a theoretical framework which could, let us know that whether there is some excess or not. So we need a consistent theoretical framework. Now the question is, which framework is best suited for such candidates? So this question has evolved over times. So earlier, like few years back, people used to constrain these models using well-motivated UV complete models. However, soon it was realized that since we do not have any good experimental significance of any physics beyond standard model at the experiments, so then these models then sort of become slightly disfavored because they were specific and they had large parameter spaces. So it was hard for them to cover broad features. So then they were soon taken over by effective field theories, which were thought of as a very good probe because model independently, by considering certain Lorentz structures, we could probe for such particles. So effective field theories are good if we are concerning for direct and indirect detection because such experiments involve low momentum transfer. But for LHC, we know that this description may fail because the momentum transfer might be close to the cutoff scale, which is being considered. So then soon, they were taken over by simplified models. So simplified models had the advantage that they were capturing broad features of UV complete models, and also they had advantage that they give consistent description if we had light mediators. So then it was sort of nice. So if we consider transition from EFT to simplified models, so we had this slight enhancement in number of free parameters because now the mediator itself became a degree of freedom apart from the dark matter. But if we compare from UV complete to sim, then definitely this number of parameters are still okay because in UV complete theories, we have many more parameters. So simplified models could be thought of as a middle ground between effective field theories and UV complete theories, and one can construct them depending on whatever spin of the mediator dark matter we are interested in to do that. So at colliders, if we want to look at dark matter signatures being described by SIMS, mostly the channel which becomes most important turns out to be the mono-jet signature. And apart from that, these mediators could be searched in their visible decays. So all of it seemed very good, but soon there were questions regarding that is the description which we are considering for collider frameworks for simplified model, is it enough? So the questions were asked on basis of certain theoretical consideration. So the first theoretical consideration, which is the most important one, was that these models are written using this electromagnetic gauge invariance times this color. So rather than the electroweak gauge invariance. Okay. So for example, let us consider a simplified model Lagrangian for a pseudo-scalar or a scalar mediated model. Now, immediately when we notice the interaction of these mediator particles with standard model quarks, we see that these interactions obey U1 electromagnetism, but they are not obeying the electroweak gauge invariance. So then, whenever we have like a limited set of gauge invariance, and maybe we are expecting that this would give rise to unitarity violation. Now, why is that so? Because we have included fewer set of particles in our spectrum, and when we'll do S stagger S equal to identity, so we are not covering the full space of particles, so then we may have unitarity violations. And then people found out that upon invoking gauge invariance back, one would get many more mono-X signatures besides mono-J. So for example, you could get enhanced mono-Higgs, mono-Z, mono-W, etc. So then, for describing these dark matter searches at LHC, from UV to EFT to simplified to less simplified models have now become sort of this thing to represent. Now let us put some limelight on how less simplified models and what are they. So suppose we want to write a gauge invariant interaction for a pseudo-scalar mediated dark matter model. Okay, so that gauge invariant interaction would necessarily involve us not only to introduce one pseudo-scalar extra, but we would also like to have one more scalar particle which is charged under SU2L. Say it's an inplet of SU2L. Because we know the standard model Higgs degree of freedom does not have any pseudo-scalar, because that gets taken away, right, through this goldstone. So then we need to introduce one more physical pseudo-scalar degree of freedom charged under this electroweak group. So that means we need more addition of particles. So a popular example is that, let us say we consider 2HTM plus pseudoscalar. But this simple example of 2HTM plus pseudoscalar itself contains 15 free parameters besides the standard model, which is a huge number, right? And in similar limelight, there have been studies of 2HTM plus C prime models. So generically speaking, if we have less simplified models, we will have many more mediators, we'll have many and sometimes more dark matters, and definitely a surge in number of free parameters. So one may argue that, okay, we can constrain these parameters, since, you know, we can put some theoretical or experimental constraints, but all these constraints are entirely model independent. Suppose I try to introduce, instead of a 2HTM, which introduces a doublet of SU2, let us introduce a spectrum where we have a triplet of SU2. So now the constraints have entirely changed. So this is very model dependent, and even 2HTM has large number of variants, etc. So then the question which we are trying to ask in our work is that when we are considering less simplified models, aren't we going back to the same complexities of UV complete models? Because there also we had so many things, and there also we could not describe things by using simple description. So clearly, that's not a good thing to do. That's because given no clear evidence. So then let us again go back to the reason of why such things was introduced. So the primary thing was gauge invariance. Now we know that theory, whatever we have written, is not electroweak gauge invariant. So upon adding more particles, unitarity would be restored. But then is standard model by itself a complete theory? It might have certain more bigger gauge groups and more unitarity violations at higher scales, right? So that shouldn't stop us from writing a simplified theory. So more concrete question which we should ask is that, is the process which we are interested in, is it getting violate, or is it violating unitarity? So this question was addressed in this earlier paper by these people, and they found out that this happens for really large couplings. So it indicated a perturbative unitarity violation rather than a unitarity violation with this addition of new states. So then their conclusion was that it is okay to use simplified models. But there is one more important thing which happens when we go to less simplified models, and that is that we add more phenological relevant channels besides mono-jet. So it might happen that, you know, at experiments, we may detect a mono-Higgs signal first and a mono-jet signal. So we may be missing on certain important channels. So it is important to not miss upon them also. But then it is also very tricky to write less simplified models. So we have to find again a middle ground of how we can do that. So then we propose a very simple method, which is actually very simple. Of what do we do, that we classify these models on the basis of additional number of relevant mediators. Okay, so by relevant we mean which may be relevant to the LHC surges and dark matter particles. So instead of considering well motivated UV complete models, we would still stick with interactions which obey electromagnetic gauge invariance, and in this hindsight that these interactions, like when written in complete model, would like be
Disha, you have 1 minute to go.
Oh, only 1 minute. Oh,
Yeah.
sorry. Okay, okay. So in the height side, that they would be electroweak gauge invariant, and then this approach would capture the broad features. So then, what do? We introduce two pseudoscalars. So pseudoscalars because they are very less constrained. Okay, and our main purpose is to see what is the effect of the second pseudoscalar. So then again, so I'm sorry, I took a lot of time, but let me tell the main question which we are trying to ask. So once we have classified that, okay, we'll add more number of particles, depending on their relevance, then the next question is that how do we compare the effect of the second mediator, or whether it is important or not. So what do? We assume that we take a benchmark where relic density plus monojet effect is dominated by the first pseudoscalar mediator only. So that means we can use single pseudoscalar mediator to describe this interaction. Then the question is that whether in this case can mono-Higgs be still relevant. So what we found out that yes, indeed it can be.
Disha?
Relevant. So a spider space from mono-Higgs constraint. So this left side plot is for single mediator, and this plot is for the mediator two mediator case. Okay, two mediator case when the monojet and the relic density is decoupled. So you see, indeed, the mono-Higgs over some parts of parameter space performs better than monojet. So even if we have relic density and this monojet signal entirely similar to the single mediator case, the effect of second mediator can be important, and hence it can be studied in terms of this simple classification models. What we further did was we further considered the effect of these constraints with higher luminosities. And you see, with higher luminosities, the parameter space gets more and more constraining. So LHC would be able to probe large parameter space close to resonance. So by the way, the region which lies below these dotted lines is allowed, because that predicts the underproduction of dark matter. So on this line, you have exact 100% relic, and below you have underproduction. So anything on this line or below is allowed. So you see, with larger luminosities, you have only these small funnel-like regions remaining to be probed. And if you have some intermediate matter dominated cosmologies, then of course it will become harder for LHC to probe. But then regions only close to funnel like regions would still remain. Apart from that, LHC can still do certain job. So yeah. Okay. So yeah, so I'll just conclude. We have presented this less simplified models using a more phenological approach and two mediator case. And what we found out was that even for the cases for relic and monojet, if we expect only single mediator case, mono-Higgs can still be important. So yeah, so thank you.